Okay, so we have discussed about the concept of temperature scale, calorimetry, that is specific heat, and latent heat of melting, latent heat of vaporization, and coefficient of linear coefficient of thermal expansion and all. Okay, similarly heat transfer, the conduction, convection, and radiation. And in radiation, we have discussed about Stefan Boltzman law, that is the black body radiation energy emitted is equal to emissivity into sigma into A into T to the power 4. Okay. And then we have discussed about Newton's law of cooling. We have discussed about Wein's displacement law, that is lambda m into T is equal to constant and all. So we have already solved some numericals. Now let us try to solve some more numericals from previous year's JE paper. Okay. So the one question is like this. Okay. Now the question is the specific heat of water. Okay. So they have given the specific heat of water. Uh, the specific heat of water is equal to 4200 joule per kg per Kelvin. Okay. 4200 joule per kg per Kelvin. Okay. This is the heat of water. Latent heat of ice, L ice, that is latent heat of fusion of ice. Okay. L ice is equal to 3.4 into 10 to the power 5, 3.4 into 10 to the power 5 joule per kg. Okay. So that's the unit of specific heat, because your heat is equal to ms delta T, right? That is the amount of heat. That is, so this is latent heat of ice is this. Okay. So the question is like this: 100 grams of ice at 0 degree centigrade. So 100 grams of ice at 0 degree centigrade is placed in 200 gram of water at 25 degree centigrade. Is placed in 200 grams of water at 25 degree centigrade. Okay. So you have some water. Okay. So you have some water which is 200 gram at 25 degree centigrade. This is water. Okay. So to this water you are adding some amount of ice. Okay. So that ice, this is 100 grams of ice, which is at 0 degree centigrade. Okay. Now the question is, how much ice will melt? Okay. The amount of ice that will melt as the temperature of water reaches the amount of ice that will melt in the process. Okay. As the temperature of water reaches 0 degree. So amount of ice that will melt as the temperature of water reaches 0 degree. So here the water will lose heat, like it will become cooler, and ice will get melted. Okay. So heat lost by water is equal to m s delta T. Okay, right? So what is the mass of water? 200 gram, which is 0.2 kg, right? Mass. Okay. Okay, then specific heat of water 4200, that is joule per kg Kelvin, and delta T is, let us say, 25. Okay, so 25 minus 0, na? Okay, so this, if you multiply, this is equal to 21,000 joule. Okay, so 4200 into 25 into 2 is 50, so that is 5. Okay, so this is 210. This much of this much of heat that is lost by water when it gets cooled from 25 to 0. Okay, now the question is, this much of heat, how much of ice will get converted because of this much of heat? Ice will get melted. So uh, the ice that will be melted, so the ice melted is equal to the amount of heat lost that will be gained by the ice. So it will be gained, heat gained, lost is equal to gained. Okay, gained divided by latent heat of ice, right? So this will be 21,000 divided by your latent heat of ice is 3.4 into 10 to the power 3 into 10 to the power 2, because it is 10 to the power 5, right? Yep. So this cancels out, this cancels out. Okay, so this becomes 21 by 21,340. Okay, so this is in kg. Okay, so you get it to be 0.0617 kg. Okay, 0.0617 kg, which is equal to 6.17 gram. Okay, sorry, 61.7 gram, which is equal to 61.7 gram. That means you have 100 gram of ice. Out of this 100 gram, some 61.7 gram of ice will get melted. 61.7 gram of ice gets melted. And still the remaining, let's say 38 or 38.3 still remain as ice. Okay, so the answer is 61.7. Okay, so there will be some numericals like this: the understanding of specific heat and latent heat, and mixing of water with ice, how much of ice gets melted and all. So you need to understand this concept of specific heat and latent heat for this. Clear? Okay. So we'll do one more numerical. Okay. So the question is like this. This is related to coefficient of thermal expansion. Okay. So this numerical is a coefficient of thermal expansion. Okay. So the question goes like this: if the coefficient of linear expansion of a metal is 0.0402 Kelvin inverse, okay, so the alpha is equal to 0.0002 Kelvin inverse. Okay, so this one we had told it earlier, like how you get it. Delta L is equal to alpha into the length into delta T. This is This is the equation. This is your change in length. Change in length. So if you draw it like this, so this is your length, and if you heat it, okay, by heating it will get expansion will be your delta L, okay, and this is L, and you are heating it by some temperature rise, so there will be a change in length which is delta L. So now, if coefficient of thermal expansion is 0.402 Kelvin inverse, then the necessary increase in temperature of metal rod in order to increase the length by 2%. That's what I was telling. So they are giving delta L by L is equal to 2%, which is equal to 2 by 100, which is equal to 0.02. Okay. So this they are given. Then they are asking what will be the maximum temperature rise. Okay. So that is equal to your alpha into delta T. Okay. So you know your delta T is equal to delta T into alpha is equal to 0.02. So we want to find out what is delta T. That is the answer actually. So this is 0.02 divided by your alpha, which is equal to 0.00002. Okay. So this delta T will become like, say, first one is 2 into 10 to the power minus 2, second one is 2 into 10 to the power minus 5, right? Minus 5. So this becomes 10 to the power 3. So 1000, right? That kind of temperature rise should be there. So these are very, very simple concepts. So if you know the formula, you can easily do it. Okay, so 1000. Okay, so this is very simple. If you remember this, you can easily do it. Okay, the only catch is you should understand what is the percentage rise they are saying. So percentage is nothing but change by original. Okay, so this is a nice numerical. This kind of numericals can come. Okay. 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 So we will try to do some more numerical. Okay. So this numerical is on Stefan Boltzman law. Okay. So this numerical is on numerical on Stefan Boltzman law. Okay. So what does Stefan Boltzman law tells? E is equal to C sigma A to the power 4, right? So this is the energy emitted. Okay. So this energy is rate only. Okay, in watt or whatever. Okay. So the question is like this. So you have two spheres. Okay. You have one sphere like this. You have a sphere like this, and you have another sphere like this. So two spheres made of same material. One has radii 1 meter, other has radii 4 meter. So one radius is 1 meter, and another radius is 4 meter. Okay. And their temperatures are 4000 and 2000 respectively. So 1 meter has temperature 4000 Kelvin. Okay. And this 4 meter radius sphere has temperature 2000 Kelvin. Okay. That's the input. And they are asking find the ratio of energy radiated per second by the first to second. Okay, so energy first, okay, energy radiated by first sphere, then energy radiated by second sphere. Okay, so this one you can write it as E1 is equal to like say emissivity same, material because remain, sigma remains same, A1 T1 to the power 4, right? Right?
Yeah.
Second sphere it will be E sigma A2 T2 to the power 4. Okay. So if you derive first, divide first by second, it will be A1 T1 to the power 4 divided by A2 T2 to the power 4. Right? So your area you know is 4 pi R1 square. Okay. So 4 pi R1 square into T1 4 divided by 4 pi R2 square into T to the power 4. So
R1 square.
So E1 by E2 is equal to R1 by R2 whole square into T1 by T2 whole 4. Right? So your R1 by R2 is equal to 4. Right?
Yeah.
This is R1 by R2 is equal to 1 by 4. Right?
Yeah.
And T1 by T2 is equal to 4000 divided by 2000 is equal to 2. Right? Here. So this will become 1 by 4 whole square into T1 by T2 equal 2 to the power 4. So one is square, other is 4. So
1 by 16 into 16.
So E1 by E2 becomes equal to 1 by 4 to the power 4 is 16.
Into 16.
Then other one is 2 to the power 4, 2 to the 8, 16. So 16, 16 cancels, so answer is 1. So the ratio of energy radiated is equal to 1. So because here area is high, area is less, but the temperature is high, that's why more radiation. Here area is high, but here area is less, temperature is high. Here area is high, but temperature is less. So this is a beautiful problem. So there can be, you can twist and you can do such kind of numerical. Okay. And okay, so one more question on Wein's law. Okay, question on Wein's law. Okay, in JE this has come. So two stars A and B radiate maximum energy at the wavelength. Okay, so this is star 1. Two stars A and B. Okay, star A and star B. Okay, two stars radiate maximum energy at the wavelength of 360 nanometer and 480 nanometer. Okay. So this is 360 nanometer and 480 nanometer. So we have two stars maybe at two different temperature. Okay. So then the ratio of surface temperature of A and B. Okay. So this is if you draw the curve, it is something like this. So let us say this is one of my star, okay, and let us say this is my another star, okay. So this star will have say temperature TA, and let us say this star has temperature TB, okay, and let us say this wavelength B, this wavelength is 480 and the other wavelength is 360, right? So you have lambda here and you have energy intensity here. So This is very simple. Lambda m into T is equal to constant. So that implies lambda m a into Ta is equal to lambda m b into Tb. Okay. So here so you want to find out just the ratio. Okay. So Ta by Tb is equal to lambda m b by lambda m a. So that is the ratio of their temperature. That's what they have asking. So lambda mb is 480 divided by 360. So 4 by 3. This is the answer. Yeah. So this kind of questions, these are very simple. So one should never leave this. Okay. And then there can be some questions related to conduction. Conduction. You have taken a picture of this? This Wein's law, this kind of question can come. Okay, then so we are discussing a lot of numericals related to radiation. Similarly, there can be questions related to conduction. So you have a iron rod and you are heating it. So this thermal conductivity of this rod is thermal conductivity. Conductivity. A is area of cross section. Cross section. L is length of the rod. Length of rod. Okay. So let us say the temperature here is T1 and here it is T2. Okay. So the amount of heat transfer from here to here. Okay. That is equal to Q dot. Okay. That is the heat transfer rate in what? K A delta T divided by the length. So this type of questions, this is using this approach you can find out. If you know this equation, suppose they will ask like at a distance of 10 meter, what is the temperature? Other things they might have given, K they might have given, area of precision they might have given. So delta T you have to find. So T1 you might be knowing. So T2, if you know delta T, you can find out what is T2. Okay. So knowing temperature at one end, what will be the temperature at other end? That kind of question will come. So in that case, you have to just find out delta T. Okay. So delta T is equal to Q into L divided by K. Okay. So the delta T is equal to T1 minus T2. It will be some number, let us say X. Right. Okay. So then T2 is equal to T1 minus X, or T1 is equal to T2 plus X. Something like that. Okay. And in conduction there can be two different situations. So you take a picture of this. Like your springs in parallel and then like your resistors and all. So there can be a condition where you have three slabs like this and you have heat is entering this side and your heat is going out that side. Okay. So so this is T1 and this is, let us say, T2, something like that. And there can be a condition where you have slabs like this. Okay, like this. So heat will go and heat will be in and heat will be out. And these materials and these slabs can have K1, K2, K3, K1, K2, K3. So in such kind of situation, the Q dot equations will be, what will be the Q dot equation? It will be so here the area of cross section remains same. So Q dot is equal to A into delta T delta T divided by sigma, let us say this is x1, like that
Length.
different thicknesses, okay? So let us say this is x2, let us say this is x3. So the equation will be like sigma x by k, okay? So this will be the heat transfer equation, sigma x by k, which is otherwise can be written as A delta T divided by x1 by k1, x2 by k2 and x3 by k3. So this if they are different material, one is steel, one is aluminium, one is nickel alloy or whatever. So if that is the case,
with different thickness.
with different material and different thickness. Okay. So that is the governing equation. And for this kind of situation, the governing equation is so for this kind of situation, the governing equation is sigma Ka, okay, sigma Ka, K, so Ki and Ai, okay, and this is Ki and Ai, sigma Ki and Ai. Here also it is Xi and Ki, right? Okay, so sigma Ka divided by delta into delta T divided by your total length. Okay, so this is x.
Same
So
thickness.
this is x. Okay, so this is x. So this what does it mean? It is like K1A1 plus K2A2 plus K3A3 into delta T divided by total length. So this is looks like a parallel and this looks like a series. So this is the driving equation for series. This is the driving equation for parallel. Okay, so take a picture. Okay, so I think I have covered in last 4 sessions. I have covered most of the things related to calorimetry, related to thermal expansion, related to temperature scale, and related to radiation, like whatever we have discussed, the Stefan Boltzman law, Newton's law of cooling, Wein's displacement law. So these 3 things, Wein's displacement law, Stefan Boltzman law, Newton's law of cooling. Out of these 3 things, if you remember, one question will definitely come. Okay, and you may have chance to get 2 questions. In that case, you will get a numerical related to coefficient of thermal expansion or calorimetry. Okay, so understanding these concepts are very, very important. Okay, these are not very complex like Cooley problems or kinematics problems in as per laws of motion and all. There it may become little bit complicated, but these are very, very simple formulas. And so numerical related to thermals and fluids one should always do. Okay. Okay. Thank you.